everyone for coming. We're going to get started. So today's ESC PhD student colloquium speaker is Nick Watkins. He did his undergraduate degree in electrical engineering at Wilkes University before coming to Penn in 2013, where he's been working with George Papa. So today he's going to talk about his work in optimal control of epidemic processes and spreading processes. So without further ado, you have the floor.
Thank you very much. Okay, so today I'm going to present work that I performed over the last couple of years on control of competitive epidemic spreading processes. So why should we care about studying competitive epidemic spreading processes? They're useful in that they give a formal mathematical model for studying a large set of interesting phenomena, such as belief spreading, which we can think of as conservative versus liberal political beliefs, or vaccination versus anti-vaccination beliefs, behavior spreading, such as the purchase of Coke or Pepsi in a market, or whether or not people like to wear pants or like to wear kilts, influence spreading, such as the effect of celebrity advocacy or platform building in politics. So today we're going to focus on a case of competitive spreading, which we can consider as a competition between two behaviors. And the behaviors that we're going to model are defection from a brand. So we're going to consider a problem in which we have two powers in a market. Each market has a collection of customers, and they're connected together by a network which spreads their behavior. Some customers which belong typically to a brand, so they're already using a brand, let's call it a particular brand of phone, might want to consider leaving their phone brand. And we would like to, as our company, stop our customers from trying the other product or stop them from defecting from this brand. So we're going to consider allocating resources in the network to exterminate this unwanted behavior in a manner that we want possible. So with respect to this example, we can consider that each node in this network is a person, and with this coloration, we'll consider that each blue node is someone that will typically use a particular phone. Let's call it a pair phone. Each red node is a person who will typically use a particular phone. Let's call it a robot phone. And the magenta nodes are somehow in the intersection between these two sets of customers. And the resources that we'd like to distribute in this context could be something like marketed advertising or better customer service or targeted discounts for products, something to that effect. So what's the structure of the remainder of the talk? First, we're going to go over the models of going to model the problem on a conceptual level. And then we'll talk about the technical details of the math and derive the results. We'll go over simulations to see if the desired effect comes out in the stochastic simulations, and then we'll draw conclusions after we've presented everything. So in presenting the model, we're first going to consider a brief review of the literature in spreading processes. Then we'll construct the process that we study from prior work and show how it might be a reasonable model for the situation. We'll go over formal mathematical problem statements and then preview the technical complications which will arise in the analysis that we'll address in the second section. So to begin the development of our model, we'll consider the most classical epidemic spreading model, the SIS model, susceptible, infected, susceptible. So in this model, we have that each node in the graph takes one of two possible compartmental values, S or I. So S stands for susceptible, I for infected. Infected meaning that this is the unwanted behavior is being displayed in the network that we want to exterminate. S meaning that we're just in the nominal state, we're behaving as expected. Now, what happens within this model, we have stochastic transitions between these compartments, and they occur as part of a coupled Poisson process. Now, what do I mean by this? I mean that if I'm a node and I'm infected with this unwanted behavior, on an average at a time 1 over delta I, which delta I is the healing rate of the node, I'm going to go from my infected state back to my susceptible state. And if I'm a susceptible node, on average at a rate of 1 over beta ij, I'm going to try to infect my neighbor j. And if my neighbor j is susceptible, he'll become infected, and if he's infected, he'll remain infected. This is a model that's been popular in studying biological diseases, but it's also been useful in studying social spreading. But So we can see that this is not suitable for our purposes immediately because we are trying to model a situation in which we have multiple behaviors that we want to extinguish. So this SIS model only has one unwanted behavior, so we need to extend it to a two-disease model. So we check the literature and see if there are any two-disease models floating around. And a few years ago, one was developed. This is the SIS model, or susceptible, infected, susceptible, infected, susceptible. And the first analysis of this was of a discrete time model a few years ago, but the analysis was heuristic, so that inspired a second group of researchers to consider a continuous time variant of the model and get tighter results, but they only considered the case in which we have homogeneous spreading rates, which means that every infection rate and every healing rate is uniform across the network, so every person goes from their unwanted behavior back to their nominal state at the same rate across the network, and infections are spread at the same rate across the network. Moreover, they limited their considerations to identical node layers. What is a node layer? In this model, we're saying that a node layer is the collection of nodes which can become infected with the unwanted behavior and all of the edges which transmit it. So this paper was just studying the case in which all of the rates are identical and also the spreading graphs are identical. So clearly, for our purposes, this doesn't quite work. In particular, the benefit of this model is that it has two infectious stages, so we can model the behaviors that we want explicitly, but the identical node layers is a limitation that we want to relax, and the homogeneous rates is a limitation that we want to relax. So we can model people leaving their brands or propagating negative advertisement about their brands, but we can't model different market population or the effect of different relationships. In particular, we should expect that some people would be particularly stubborn, so if they find something very bad about their phone and they want to propagate negative advertisement very aggressively, they're going to stay in their aggressive state for a long time, but some people might be very mild, so they'll transition back to their unaffected state very quickly. So we need to capture that by having heterogeneous healing rates, and some people might be very influential over their neighbors, whereas some people might not be very persuasive, so we need to capture that by introducing heterogeneous spreading rates. So this is the extension of the model that we'll analyze in the remainder. As you can see, we give each infection its own graph. So in here, we're saying that the red edges spread the red phenomenon, the blue edges spread the blue phenomenon, and magenta edges spread both. And we give each node its own healing rate and each edge its own infection rate. So what is the first problem that we're going to consider? The first problem is the minimum budget control problem. So it's stated in this problem, we have an instance where we have the structure of both networks. So we know how the spread of A is structured and how the spread of B is structured. And we take the stance of competitor A, and we say that we can observe B's network, and we assume that it's fixed. And we say, can we use the knowledge of their network to design our resources so that we can exterminate the unwanted behavior optimally? So this is not a competitive allocation problem in the sense that we're not considering the case where we're finding a Nash equilibrium necessarily. We're just saying, can I compute this optimization tractably if their resources are fixed? The second problem that we'll consider is if I don't have unlimited resources, but I have a fixed budget, can I do something to mitigate the unwanted behavior, not necessarily eliminate it? So suppose I have a fixed budget, but it's not enough to exterminate the unwanted behavior. Can I still allocate resources in a way that will remove the unwanted behavior as much as possible? So heuristically, this is the problem of, given my budget, how long can I keep my customers loyal? How much of this unwanted behavior can I exterminate? And so now we need to consider the technical complications which might arise when we're trying to analyze this model. The first is that we have a need for approximation. So those among you who followed the development of the model very quickly might notice that it's really just a continuous time Markov process. So we can actually represent this as a linear system in a high dimension. But the problem is that the dimension is too high. So to write the linear system dynamics for this process, you would need on the order of 3 to the n states. So we very quickly run out of analytic resources, and we very quickly run out of computational resources. So we need to use some approximation technique to reduce the dimension of the problem. Luckily, on some level, there are there are techniques that are used commonly in this literature for approximating and doing dimensionality reduction. However, the caveat there is that the accuracy of these approximation techniques is not well understood in general. So we have, going forward, a model where we know that we can approximate it, but not necessarily at zero loss. So that's something that we'll come back to when we see simulations. And the second problem that we'll need to address technically is that we need the problem to be convex in order to solve it tractably. And in general, this would not be a convex problem because we need to enforce a stability condition about the dynamics. So we have eigenvalue constraints in our problem. Yes?
How is the budget applied? Does it change the rate of infection or does it change the status of the node?
So the budget is applied, good question. The budget is going to be applied to change the infection and healing rates in the network, not change the states. So that would be a different problem, but interesting. Okay. So in other words, the natural problem statements for these are always going to be non-convex, so we have a very poorly structured feasible region. But using tools from network theory like the Perrin-Frobenius theorem and tools from convex optimization like geometric programming, we can show that there's an equivalence between the original problem and a convex problem. Okay. So now we'll move on to the portion of the talk that's more technical in nature, and we'll begin by deriving the approximate dynamics we'll study from the original process so to see where the approximation is made so that we have some intuition as to where things might go awry when we look at the simulations and where the interesting phenomena might occur. Then we'll analyze the stability of the nonlinear dynamics to find conditions in which the behavior that we want is realized. Then we'll interpret these stability conditions to see if we can say anything analytically about the benefits of competition. And then we'll convexify the problems so that we can actually compute these allocations tractably. So to develop these dynamics, we first need to develop some notation. So let x sub I superscript a just be an indicator that node I is infected with disease A. It takes values 0, 1, 0 if it's not infected with disease A, and 1 if it is infected with disease A. Likewise, we'll let x subscript I superscript b be an indicator of infection B. X sub I superscript s be an indicator of state S. And we use this notation in this graph, yi to be the effective infection rate for A, just being the sum of all the infected neighbors at the time. And similarly, yi superscript b to be the sum of all the infection rates of the neighbors at the time. So with this notation, we can write the dynamics for process A with this expression. I'm not going to go through the full derivation analytically, but just intuitively, you can look at this as being flow balance. So if we look at state S, if we're in state S, we're going to flow into state A, or compartment A, at a rate given by the effective spreading rate, which is just the sum of all the infected neighbors. And if we're in state A, we're going to flow out of state A at a rate given by the healing rate. Likewise, we can write down expressions for the dynamics of B and the dynamics of the susceptible state. So obviously, these expressions are very complicated and hard to analyze. So we need to make some assumptions to reduce the dimension, for one, and also to make the analysis tractable. So at the beginning, if you recall, I said that we can write these as a linear system, but we actually have a nonlinear system here. But the reason is that we have equations which are developed to be represented in a space that grows linearly. So the dimension of this representation of the process is 3n as opposed to O of 3 to the n. And the second observation that we can make is that we actually don't need all three states being represented explicitly. So in particular, the dynamics for process or state S are redundant with the dynamics for state A and state B. So we can just make the substitution 1 minus A minus B for S and recover a slightly more compact set of equations. And once we do this, if we expand the expectation over the sums, we see that we have expectations of products. And this wouldn't be a problem if we can represent the dynamics of the expectation of the products in terms of the expectations of the variables themselves, but we can't. And in particular, if we write down expressions for the dynamics of the expectations of products of two variables, we'll see that they'll include the expectations of products of three variables, and the dynamics of the expectation of products of three variables will include the expectation dynamics of four variables, and so on. So if we continue with that process, eventually we'll include all the variables in the system and end up again in a high-dimensional space. So in order to make this model tractable, we need to make a simplifying assumption, and the one that's common to the literature is that we represent the expectation of the product by the product of the expectations. Now, this is implicitly making the assumption that these variables are uncorrelated, and it's clear just by construction that they're not. So obviously, there's going to be some error somewhere. And the only hope is that it's not that much, which is, again, something we'll come back to in simulation. So just to summarize this derivation, what we've done is taken a system which can be represented in a very simple space, but a very large space, and projected it into a very small but very complicated, or somewhat complicated space. And we've also lost some details about the accuracy of the process in the analysis of doing so. So this is the result for the stability of the nonlinear dynamics. It turns out that the equilibria, the set of equilibria that we want to stabilize, are locally exponentially stable if and only if the linearized dynamics about the equilibrium are stable. And this gives us a lot in terms of the resource design problem, because...
Are you saying the nonlinear stability of the equilibrium is if and only if
yes.
the exponential stability?
Yes, yes. So if this...
Because the linear model upper bounds.
No. The nonlinear mean field dynamics are locally exponentially stable if and only if the linearization of the nonlinear dynamics are stable. So actually, I mean, this upper bound that you're alluding to for the SIS process doesn't hold in this case.
So you're basically just stating Hartman-Grobman theorem. You're saying if you linearize the stability of the linear.
So that would just give stability, but I mean, this is exponential stability.
Oh, okay.
Yeah.
So you're saying the nonlinear one is
locally exponentially stable. Yeah. Yes.
If the linear one
yes.
is exponential.
Yeah, I mean, linear one is exponentially stable, which is just stable, so yeah. Okay, and this is helpful for our problem because if we look at the structure of the linearized system, we have this block triangular structure, and we can show that this JB block corresponds exactly to the linearization of a single virus model. And there's prior literature which shows that this linearization of the SIS model, the single disease model, is always exponentially stable. So this JB block is always stable. So we actually only need to design this matrix so that the JA block, which is given by this expression, is stable. So that simplifies consideration. Yeah.
So what are the equilibria?
Oh, okay. Actually, I skipped over that. Cool. Thank you. So the equilibria that we're considering in this case are that, so we're just, the problem, if you recall, is that we're observing the competitors' states, and then we're designing our own. So the equilibrium that we're considering is that we're extinguishing the unwanted behavior on our network, but we're letting the other unwanted behavior, so my competitor's unwanted behavior, propagate. So in other words, in the context of this problem, it would be I'm stopping bad advertisements on, or bad word-of-mouth advertising on my network, but I'm allowing my competitors' customers talk bad about their product. I'm not trying to control their process.
My question is, if we let the system, let's say the nonlinear or the linearized system run, right?
Mm-hmm.
Then what's going to be the equilibrium then?
The linearization, so it will be the first, so all the states corresponding to process A will be 0. And then as a function of the parameters of the oppositions network, you'll have a steady state realized. So if your competitor's network is such that their behavior is eliminated, then they'll also be 0. But if it could be possible, and in general is possible, that their states will be non-zero. So to answer your question, it'll be the variables corresponding to us will be 0, and then in general, the variables corresponding to the opposition, the opponent's process will be non-zero in general. Okay? Okay. Okay. Okay, so now we'll see if this structure gives us anything analytically. And the answer is yeah. So if we look at the SIS dynamics directly, so this would be the case in which I'm designing dynamics ignoring my competition completely, the stability condition is that this matrix, the leading eigenvalue of this matrix, is in the left half of the complex plane. For the SIS stability, we have essentially the same matrix, except all the non-negative values are being scaled by something that's a quantity that's a function of my neighbor's steady states, my opposition steady states, the steady states of process B. And since we can show analytically that all these states must be between 0 and 1, then the scaling factor is always between 0 and 1. So I'm compressing all of the effect of considering competition is that I'm compressing all the effective infection rates. And you can show analytically that the SIS stability condition implies the SIS stability condition. And also you can show that they're usually, meaning that whenever my competition steady states are non-zero, I can actually allow parameters of my system to be more aggressive, which is nice. So I have some, I'm always guaranteed, as long as my competition is not eliminating their unwanted behavior, that I can have a more aggressive disease propagating on my network and still eliminate it. So in short, yes, we can use these conditions, and we should always expect that there's improvement. So now we get to the computational portion of the talk, in which we're just showing that these problems are convex, or we can convexify these problems. So this is the formal statement of the budget minimization problem. We're just minimizing the sum of all the costs of all the allocations subject to the stability constraint. And the non-convexity is coming from the constraint. Likewise, in the rate minimization problem, we're minimizing the leading eigenvalue of the disease that we're designing, or the network we're designing, subject to a total budget consumption constraint. So we're given C dollars, and we're making sure that we spend no more than C dollars, and we want to try to make the leading eigenvalue of JA as small as possible. Now, this is not formally a rate of the process, but it's just a heuristic that we hope should control the process well. And we show in simulation that in the mean field regime it does. So now in order to present the convexification of the problems, we need to introduce some technical background, the first of which is on geometric programming. So geometric programs are just quasi-convex programs which can be convexified by a change of variables and monotone mapping. In particular, we have that the objective functions are polynomials, which are sum of monomials, and monomials are a product of non-negative variables with non-negative coefficients raised to real powers. We can also allow for polynomial inequality constraints, monomial equality constraints, and at the end of the day, we get back log sum exponential functions. But the catch is that everything must be positive. All of the variables and all the coefficients must be positive. And the second tool that we need analytically is the Perrin-Frobenius theorem. And simply stated, this is just that if we have a non-negative matrix, then we're going to have a unique non-negative eigenvector, which corresponds to the an eigenvalue which is the spectral radius of the matrix. And we can use this in designing network structures. And we're going to use this to replace the eigenvalue constraint. So just to be concrete, we'll go through one problem and do the transformation. So we start with our non-convex problem. We look at this constraint and say it's non-convex. What can I do? Now we look at the structure of this JA matrix and note that it's a Metzler matrix, meaning that all of the off-diagonal components are non-negative, and the only negative components are on the diagonal. And so we say, well, what can we do to change this? Well, if we impose that we have an upper bound on all of these diagonal elements, so we're saying that my healing rate is bounded by some constant that I can choose arbitrarily large, I can add that constant times the identity to it, and then shift this Metzler matrix to be a non-negative matrix. Once I have a non-negative matrix, I can take this eigenvalue constraint and replace it with an eigenvalue equation, and then try to enforce a constraint on this equation so that I can get a tractable program back. So after shifting these expressions around analytically, if I replace this with an inequality, all that I'm left to do is to show that in this expression, I have non-negative constants and non-negative variables, and that I meet this inequality with equality at any optimal solution. So in particular, after I expand this matrix multiplication out, I see that the only negative variables are coming from this term, but this term is always positive. So if I define a new variable, t, and then now I have a positive variable there, and I know how to map it back to my original expressions. And now I still have this inequality constraint. But if I make the assumption that these Fij functions are all monotone decreasing, then I can show that at any optimal solution, this inequality is met with equality. So I have, in fact, the eigenvector equation back, and so that I can design this eigenvalue so it meets the stability criterion. The reason for this is just by observation. If this inequality is strict, meaning that this is not met with equality, then if this is monotone decreasing, I'm always going to make beta ji bigger to make this inequality. So in summary, we use the geometric programming and the Perrin-Frobenius tools to shift our non-convex problem into a space where the problem is convex, and then we use those the inverse of those transformations to get back the solution to our original problem, and we can solve it tractably. So now we'll move on to the simulation of the process. And first, we will have a simulation showing that when it loads. Yeah. So the Fij functions all just had to be monotone decreasing polynomials. G just had to admit a transformation which made it polynomial in the new variable. So G as a function of t has to be a polynomial. But G as a function of delta is just a shifted polynomial, which is something like the class of functions which that emits is something like a shifted polynomial. So it's very general. Okay, so now we have. So here's a simulation of the process when we just have arbitrary parameters plugged in. So the reason that we want to see this is qualitatively, will these behaviors live long if we don't do anything to control them? And if we look at the simulation, we show that both behavior A and behavior B exist in the network for a very long time. You can show analytically that they will, with probability 1, they will eventually die out, but you can also show analytically that they will last for a very long time. So let's see what happens when we apply our control. So when we apply our network design control, or we apply our resource allocation, you can see that behavior A dies out in finite time and will stay dead forever. And behavior B persists. So it's nice that actually our algorithm designed a network in which we got the behavior back that we wanted to begin with. But now let's ask more quantitative questions of our simulations. And first, did we actually gain anything from considering the heterogeneous case over the homogeneous case? And the answer is yes. This graph is normalized to the homogeneous threshold so that the value 0 is the transmissivity value, which is just the ratio of the infection rate over the healing rate. If we impose the condition that all the edges for a particular node have the same infection rate. And this threshold 0 is just if I have a homogeneous network, this is the threshold that I would need to attain to have stability. So here we see about half of our nodes are actually above this threshold, and if we check the graph for this simulation, all of these nodes are in the competitive layer, meaning the intersection between process A and process B. So whenever there's competition here, we can actually afford more aggressive parameter selections. The second condition that we might want to investigate with simulation is, are our conditions tight? Meaning that are the solutions of our problem, do they generate solutions that are on the border between instability and stability? And the answer is, in general, yes. So again, if we look at this solution, we see if we scale the aggressiveness of this disease by any factor greater than 1, we get that the disease lives in the mean field steady state. And if we scale it by any factor less than 1, it stays dead as we would expect it to. And the third question that we might want to ask is this proxy that we use, this leading eigenvalue, a good controller of the steady state persistence of the disease? And in general, it seems yes. So again, if we are given the optimal budget, so I'm normalizing this budget with respect to the budget that we get back from the budget optimization problem. If we're given that, then we realize stability, or we realize stability of the desired equilibrium. But if we have any budget that's less than that, then the unwanted behavior lives for a long time. And if we have any budget that's greater than that, we also get back a solution which kills off the process as we would like. Now, the most interesting question that we can answer through simulation is whether or not this mean field approximation gives us a good representation of the process, the stochastic process. And it's a more complicated question, but thankfully, the typical case when we use our design algorithms is that it does seem to work well. We can't really say that analytically, But we can see that in every instance that we've tried, we actually get that the process dies out, and it dies out quickly. And the intuition that I suspect might be true is that when we design the network to kill off process A, process B will eventually recover the SIS dynamics, and it's well accepted that the SIS mean field approximation is a good approximation for SIS, although it's not necessarily shown formally. However, if we just take a random instance of the problem, so if we choose random graphs with some intersection, and we choose the parameters just being uniformly at random from these intervals, the infection rates being from 30 to 30.3, and the healing rates being from 15 to 15.5, we see that in general these mean field approximations might be very bad. So why do I say this? Because this is a typical instance of this simulation, which is a very mild circumstance where we have the 60% confidence intervals span basically the entire space. So we're saying, okay, anything could happen, and the mean field approximation at the end of this time horizon is off by 20%, which is quite a lot. So at the end of the day, what is it that we can say about our problem originally? Well, we can say that if you give me all these functions in the network, then I can tell you that in the mean field regime, I can exterminate this process exponentially quickly. But we're not sure if that is representative of the original stochastic model. So where does that leave us with respect to future work? Well, we can consider problems where we have competitive allocation, where we're trying to game, and we know we're trying to anticipate how our competitors are going to respond to our actions. And we can have multi-pathogen models where we are considering more than 2 diseases. But I think the more interesting questions for future work are hinted at by this gap between the mean field approximation and the stochastic process. So I think an important question for these epidemic spreading models going forward is understanding the gap between the mean field approximation, which it's clear that we need to make some approximation in order to make the analysis feasible, the analysis tractable. But it's also clear just through simulation that in perfectly reasonable cases that the mean field approximation doesn't give us much information about the stochastic process. So more work needs to be done there. The other possibility for future research is just to relax the need for an analytic approach and consider data-driven approaches. So something that's being done more on the biological epidemic side of this literature is just saying, well, I have some data on the spread of this disease. Can I use this data to make smarter decisions? Does it necessarily involve a network model? Sometimes yes, sometimes no. But maybe if we can't say anything about the network model, this is a feasible approach that's more practical for the biological epidemic community. Okay, and that's everything that I have.
Does this framework admit heterogeneity in terms of functions f and g?
I'm sorry, I missed the beginning of your question.
What if the functions f and g are different for each ij?
Yeah, that's fine. Yes. Yep. Yeah.
So in your simulations, you show that this mean field can be very off.
Yes.
Sometimes, but it wasn't clear to me. In the previous picture before that, your mean field was actually looking at it.
Oh, sorry, wrong way.
It's like an upper bound.
Yeah. So
what's the difference between these two?
So actually, in this case, it's not an upper bound or a lower bound. I mean, you can show that. So this, I mean, just by symmetry here, I mean, it's a lower bound for B and it's an upper bound for A in this instance. So if we flipped everything, then it would be the other way.
But what is different between this picture, this
So
here,
yeah.
and the next one?
So this set of simulations is a typical result of what happens when we apply the network design algorithms that we developed. So it just so happens that when we use this, typically everything works the way that you would like it to. I mean, is this analytically provable, or can we demonstrate anything about this analytically? Not really, but just it so happens that, yeah, very typically if we design the network to eliminate one of the diseases, then that disease dies off, and the other one eventually recovers the SIS dynamics, which there hasn't been any necessarily a formal result showing that those SIS dynamics are a good approximation of the SIS process. But in general, it's well accepted that it is. So And that, I think, is what we're seeing here. It's just an artifact of the problem that we've asked. Or as opposed to that if we take random parameters, then, yeah, anything can happen.
One more question, perhaps related. So apart from examining the mean of the process, right?
Mm-hmm.
Do you know what happens if you look at other statistics?
You mean like second order moments, third order, like?
Yeah, or maybe some tail probabilities or something. I'm not sure exactly what would be the right statistics, but I'm wondering, first of all, whether there is work on considering higher order statistics.
So there are some works for SIS considering the moments of the second dynamics. So they, instead of cutting it off after products of 2 variables, they cut it off at products of 3 variables. However, actually in that case, if you do the approximation naively, which you can get mean field approximations which don't even stay bounded in the 0-1 interval. So I mean, not only are they not probabilities, but they're not even values that can be probabilities. But you can create systems using higher order moments that will stay bounded if you're clever, but it doesn't mean that your approximation is better. You're just introducing error differently. You're not necessarily introducing any less error.
I have a related question. So I guess rather than controlling the mean process, do people ever try to directly deal with the stochastic system and apply stochastic control?
So I remember seeing a paper on SIS about using controlled Markov, like a Markov decision process, sort of. The issue there is dimensionality, right? So, I mean, if you consider it just as a Markov process in a high-dimensional space, then the dynamics grow exponentially. So, I mean, you can do it, but it's not computationally effective. And, I mean, it's arguable if you get any benefits from that approach, because all of the approaches are algorithmic. You can't say anything analytically.